Andromeda Galaxy, future collision with Milky Way. In the darkened vault of the northern sky, beyond the veil of our own spiraled stars, lies a shimmering neighbor that has watched us in silence for billions of years. Known to astronomers as the Andromeda Galaxy, it stretches across space like a soft brushstroke of light. To the naked eye, it appears as a faint smudge in the constellation of Andromeda, but in truth, it is a sprawling titan, a vast elliptical spiral brimming with hundreds of billions of stars, nebula, and hidden mysteries. Spiral galaxy to our own Milky Way, yet still separated by more than 2 million light-years of emptiness. And yet, it is coming. Slowly, invisibly, but with certainty, it moves toward us through the vast cold of intergalactic space. The Andromeda Galaxy is larger in diameter than the Milky Way, but comparable in mass. Its gravitational pull, tugging delicately yet relentlessly across the void, has been drawing it nearer to us for eons. Long ago, astronomers assumed it was just another faraway object, another distant point of light in the night sky. But with the advent of modern spectroscopic instruments and the analysis of redshift and blueshift, scientists discovered that Andromeda was not retreating, it was advancing. It is one of the few galaxies in our universe that is moving toward us rather than away. This blue shift in its spectral lines marked a turning point in our understanding of cosmic dynamics and our place in the galactic neighborhood. Andromeda is moving toward the Milky Way at a speed of approximately 70 miles per second. That pace may seem glacial on human timescales, but in the rhythm of galaxies it is swift and decisive. The collision course it follows will culminate in a dramatic and beautiful merger of two galactic giants. An event that, while silent in space, will forever change the structure of our sky. Though this grand encounter is not expected for another 4 billion years, the inevitability of it is beyond doubt. Simulations suggest that when these two spirals collide, their mutual gravity will warp and twist their elegant arms into chaotic shapes. Stars will be slung across space in great arcs, their orbits shattered and reshaped by new gravitational patterns. However, despite the scale of one at the core of the Milky Way and one deep within Andromeda, are expected to spiral toward each other in a titanic gravitational dance, eventually merging into a supermassive black hole of unimaginable mass. The galaxy that will emerge from this cosmic union will likely not resemble either of its parents. Astronomers believe the end result will be a large, elliptical galaxy, its graceful spiral arms smeared and lost in the merger's chaos. Some have already given it a name: Milkomeda, a blending of Milky Way and Andromeda. Though our sun may still exist when this event unfolds, its light will be nearing the end of its life. Earth, if it remains habitable at all, will be under a very different sky, one filled with streaks of stars, gravitational streams, and glowing remnants of a galactic rebirth. Andromeda's impending arrival is more than a celestial spectacle. It is a reminder that the cosmos is in motion, that even seemingly eternal structures evolve and collide. It challenges our sense of permanence and stillness. Galaxies are not fixed points in a static universe. They are islands adrift in the dark, destined to interact, merge, and change forever. The story of Andromeda is not just the tale of a future event. It is a window into galactic evolution, a living experiment, unfolding on timescales far beyond human experience, but now fully within our grasp. To understand Messier 87's supermassive black hole, as we contemplate the distant destiny of our own galaxy, its slow millennial collision with Andromeda over the coming eons, we begin to understand that galactic interactions are not just structural transformations. They also awaken the dormant giants that lie at the heart of galaxies. Supermassive black holes, these colossal entities, often silent for millions of years, can spring to life during mergers, devouring gas, stars, and even light itself. And to truly grasp the power and mystery of these objects, one need only turn their gaze to a massive, elliptical galaxy residing in the constellation Virgo, Messier 87. Messier 87, or M87 as it is commonly known, sits roughly 50 million light-years away from Earth. It dominates the Virgo cluster, not only through its staggering size, but through the monster that lies at its core. This galaxy is immense by every measure, home to trillions of stars and an extended halo of globular clusters that swirl like fireflies caught in a gravitational tide. But it is the central object, the black hole, that has become a beacon of modern astrophysics and a symbol of human curiosity reaching across space. For decades, astronomers suspected the presence of something extraordinary at the heart of M87. They observed stars and clouds of gas behaving in ways that defied Newtonian expectations, accelerating around an invisible center, vanishing into what appeared to be nothingness. Only a supermassive black hole could account for such behavior. Estimates of its mass were staggering, several billion times the mass of our Sun, compressed into a region no larger than our solar system. But no one had ever seen a black hole directly. It was only through its gravitational fingerprint that its existence could be inferred. That changed in the spring of the year 2019, when the Event Horizon Telescope, a global network of synchronized radio observatories, captured the first image of a black hole's shadow. After years of planning, computation, and coordination across continents, the blurry orange ring emerged into public consciousness. A glowing halo of light bent by gravity, surrounding a shadowed center that marks the event horizon. That image did not simply confirm theories, it ignited them. The object in that image was M87's black hole, now immortalized as the first black hole ever visually captured. The science behind this image is profound. Light emitted by superheated gas spiraling into the black hole is bent by gravity to form a ring of fire around the darkness. The shadow itself is not the black hole, but the absence of light, where no radiation escapes, no matter the frequency. It was the ultimate silhouette traced by matter dying in motion, its atoms shredded by tidal forces, its photons flung into curved paths dictated by Einstein's equation. The image provided tangible confirmation of general relativity in one of the most extreme environments known to physics. But M87's black hole is not merely a still image. It is an active, violent engine. It spews jets of high-energy particles, tens of thousands of light-years, into intergalactic space, powered by magnetic fields twisted by the black hole's rotation. These relativistic jets, as they are known, are among the brightest phenomena in the observable universe, visible across radio, optical and X-ray wavelengths. They pierce the surrounding galactic medium and shape the evolution of stars and gas around them. Entire regions of the galaxy are sculpted by the energy this one object releases. In studying M87's black hole, scientists also gained insight into how galaxies form and evolve. There is growing consensus that nearly every large galaxy harbors a supermassive black hole at its center, and that the growth of these objects is intimately tied to the development of their host galaxies. The jets, winds, and radiation from active black holes regulate star formation, influence galactic shape, and prevent runaway collapse of interstellar gas. M87 offers a window into this cosmic feedback process. showing not just what black holes consume, but what they create in return: structure, order, and balance. Even today, the black hole at the heart of M87 continues to be observed and studied. New instruments, including the next-generation Event Horizon Telescope and space-based observatories, aim to reveal changes in the structure of its glowing disk, shifts in its jet emission, and possibly even signs of material orbiting near the point of no return. For now, it remains a silent architect of its galactic kingdom, holding court in a space where light itself bows to gravity. And if we follow the path carved by M87's black hole, from image to theory, from jet to structure, we find ourselves inevitably drawn into even darker territory. For there are places where galaxies do not gather, where stars are rare, and where the very fabric of the cosmos seems stretched thin. These are the voids, the empty places between, and among them lies one of the strangest of all, the Bootes void, the great nothingness. As we drift beyond the luminous swirl of Andromeda's inevitable embrace, and past the gravitational giant of Messier 87's heart, we find ourselves staring into an abyss so vast and silent that it challenges the very nature of existence. It is here, in a corner of the observable universe, that we encounter the Bootes void, a cosmic enigma so immense and so eerily empty that astronomers once questioned whether our understanding of the universe was fundamentally flawed. Discovered in the late 20th century during a survey of galaxy distributions, the Bootes void appeared as a glaring hole in the tapestry of the cosmos. This region, spanning hundreds of millions of light-years, contains a fraction of the galaxies expected in a volume of such scale. In a universe where matter tends to cluster into webs, filaments, and superclusters, the void stands as a contradiction: vast, dark, and unsettlingly barren. The Bootes void challenges the assumption that the universe is evenly filled with galaxies on large scales. Instead of the dense structures seen in places like the Virgo supercluster or the Perseus-Pisces filament, this region seems abandoned, as if cosmic architects left a space unfinished. Some scientists refer to it as a supervoid, a term that underscores both its immense size and its deviation from expected galactic distribution. And though some galaxies have been discovered within its bounds, they are few and far between, like flickering campfires scattered across a frozen desert. What makes the Bootes void even more mystifying is not simply its emptiness, but what that emptiness implies. It raises questions about the distribution of dark matter, the mysterious scaffolding upon which visible matter clings. Did dark matter somehow fail to seed galaxies here? Or did galaxies form and then migrate away over billions of years due to gravitational dynamics we have yet to understand? These are questions without definitive answers, feeding both scientific curiosity and existential reflection. The void's sheer scale boggles the mind. Light itself would take hundreds of millions of years to cross its expanse, meaning that any message sent from one side to the other would be older than the earliest complex life forms on Earth by the time it arrived. Within this emptiness, time feels stretched, and the idea of motion seems pointless. It is a realm that defies not only expectations, but also the senses, where the normal rhythm of cosmic evolution appears to have faltered, or perhaps never began. And yet, this emptiness is not completely without purpose. The Bootes void has become a vital tool for astronomers studying the large-scale structure of the universe. It serves as a contrast, a control sample against the galaxy-rich environments found elsewhere. By analyzing its characteristics, researchers gain insights into the evolution of cosmic structures, the behavior of dark energy, and even the limits of inflation theory from the early universe. Even within its silence, the void speaks, if not in sound, then in implication. It tells us that the universe is not only a place of blazing stars and spinning galaxies, but also one of profound stillness. In its darkness, we see the boundaries of human understanding and feel the cold breath of a cosmos that still holds secrets. As we continue our journey across this grand celestial sea, we now shift from silence to signal, from emptiness to the pulsing rhythm of a different kind of cosmic phenomenon, one born from cataclysm and spinning with perfect precision, the pulsar Sagittarius A, the dark heart of the Milky Way. From the silence of the Boötes void, where galaxies are few and darkness reigns, we now plunge into the gravitational furnace at the very center of our own cosmic home. Here, in the densely packed core of the Milky Way, lies a force so immense, so mysterious, and so ancient that it bends both space and time to its will. It is Sagittarius A, the supermassive black hole that anchors our galaxy with an invisible hand of gravity, shaping the orbits of stars, sculpting galactic structure, and offering a glimpse into the very limits of physics itself. Located roughly 26,000 light-years from Earth, in the direction of the Sagittarius constellation, this gravitational behemoth lurks behind a curtain of gas, dust, and stellar debris. For much of human history, its presence was unknown, hidden not by distance, but by opacity. It was only in the latter part of the 20th century, through advancements in radio and infrared astronomy, that astronomers began to suspect a massive object sat at the galactic core. What they found was not simply large, but colossal. A mass equivalent to over 4 million suns, compacted into a space smaller than our solar system. Sagittarius A exerts such powerful gravitational influence that nearby stars, like the now famous S2, whip around it in elongated orbits, reaching blistering speeds as they approach its event horizon. These stellar orbits have been critical in confirming both the existence of the black hole and its mass. Decades of observation, especially from observatories in Chile and Hawaii, have allowed astrophysicists to map the region in stunning detail, turning theory into tangible reality. The existence of Sagittarius A offers more than mere confirmation of Einstein's predictions. It presents a natural laboratory for testing the extremes of general relativity and quantum mechanics, two pillars of modern physics that often clash at the fringes of black hole science. Unlike stellar mass black holes formed from collapsed stars, Sagittarius A is a supermassive entity whose origin remains one of astrophysics' greatest puzzles. Did it grow from the accretion of gas and stars over billions of years? Or did it form in a single catastrophic collapse in the early universe? The answer lies deep within its darkness, guarded by the event horizon, from which not even light can escape. In April of 2019, the Event Horizon Telescope collaboration made history by capturing the first image of a black hole's shadow. Though that image was of the behemoth in the Messier 87 galaxy, the same techniques were later applied to Sagittarius A, and in May of 2022, humanity glimpsed its own galactic anchor. The image revealed a glowing ring of radio emissions, warped and stretched by the immense gravity of the black hole's surrounding. It was a cosmic mirror, reflecting not light, but our own desire to understand the universe. Yet Sagittarius A is not merely an astrophysical curiosity. It is a force that has shaped the Milky Way's past and will influence its future. The gravity well it creates helps to organize the orbits of hundreds of billions of stars, providing stability to the galactic disk. It is also suspected of playing a role in the dynamics of star formation, either triggering the birth of new stars through shock waves or quelling it by heating and dispersing interstellar gas. More enigmatically, black holes like Sagittarius A may be responsible for the powerful jets of particles observed in other galaxies, jets that shoot across intergalactic space for hundreds of thousands of light years. While our black hole currently lies dormant, swallowing matter with relative subtlety, it may have once flared brightly as a quasar, emitting high-energy radiation across the cosmos. Some astronomers believe it could awaken again, perhaps triggered by an influx of gas or a collision with another galaxy. Our understanding of Sagittarius A continues to evolve, shaped by instruments like the Chandra X-ray Observatory and the Very Large Telescope. Each year brings new insights into its spin, its accretion patterns, and the extreme physics at its core. But for all we have learned, what lies beyond its event horizon remains a mystery. Is it a singularity, an infinitesimal point of infinite density, or could it be something more exotic? Perhaps a gateway to another region of space, or even a parallel universe. As we leave the turbulent center of our galaxy behind, the pool of mystery does not loosen its grip. Instead, it redirects our gaze toward another celestial marvel, one that pulses with uncanny regularity and astonishing power. We now turn toward the rhythmic lighthouse of the universe, where collapsed stars beat like cosmic hearts across the fabric of space-time. The pulsar. Amidst the spiraling arms of our galaxy, where Sagittarius A casts its influence from the darkened core, there lies another relic of cosmic violence. An ancient remnant of a stellar explosion that once lit up Earth's skies nearly a millennium ago. This remnant is known as the Crab Nebula, a celestial monument to the raw, explosive power of a supernova. Unlike the silent, invisible pool of a black hole, the Crab Nebula is an extravagant display of light and motion, an expanding shell of stellar debris that continues to reshape our understanding of stellar death and rebirth. Roughly 7,000 light-years from Earth in the constellation Taurus, the Crab Nebula emerged from the violent death of a massive star. When the star reached the end of its life, it underwent a supernova explosion, one of the most energetic events in the universe. Ancient astronomers from China, Japan, and the Middle East documented a brilliant new star in the sky in the year 1054, visible even in daylight for weeks. What they witnessed was the birth of the Crab Nebula, a supernova whose radiance pierced the heavens with an intensity that defied imagination. Today, centuries later, its glowing tendrils of gas and dust continue to expand at astonishing speeds, painting a cosmic tapestry in motion. At the heart of this nebula lies a pulsar, a rapidly rotating neutron star, the collapsed core of the original progenitor star. This pulsar, only about the size of a small city, yet possessing a mass greater than that of our Sun, spins 30 times per second, emitting beams of electromagnetic radiation with each rotation. It is a cosmic lighthouse, flashing across space with rhythmic precision, powered by the immense energy of its spin. The Crab pulsar is not only a source of intense radiation, but also a natural laboratory for physicists seeking to understand the behavior of matter under the most extreme conditions imaginable. Its powerful magnetic fields and energetic winds create a complex dance of particles and fields that has captivated astronomers for decades. The filaments of the Crab Nebula composed of ionized gas, stretch outward in intricate patterns, each glowing with the energy from the pulsar's radiation. These gases, primarily hydrogen, helium, and heavier elements forged in the heart of the dying star, are dispersed into the interstellar medium, enriching it with the ingredients necessary for new stars and planets. In this way, the Crab Nebula serves not only as a record of stellar death, but as a promise of cosmic renewal. From destruction comes creation. The heavy elements produced in such explosions are essential for rocky worlds, atmospheres, and even life itself. Moreover, the Crab Nebula holds an important place in human scientific progress. It was one of the first celestial objects studied in the newly emerging field of radio astronomy in the mid-20th century. It also became a key calibration source for X-ray telescopes and a benchmark for understanding pulsars and high-energy astrophysics. Its brilliance across multiple wavelengths, from radio to gamma rays, makes it a cornerstone of observational astronomy, continuously revealing new layers of complexity as technology advances. In studying the Crab Nebula, scientists have come to realize the intricate interplay between massive stars and the galactic environment. These supernova remnants act as both destroyers and creators, ending the lives of stars while seeding the galaxy with the raw materials of future solar systems. They also drive shockwaves that compress nearby gas clouds, triggering the birth of new stars. Thus, the Crab Nebula is not merely an echo of an ancient explosion, but an active participant in the ongoing cycle of stellar evolution. As we journey through space, from the vast voids of Boötes to the dense gravity of black holes, the Crab Nebula stands as a visual and scientific reminder of the universe's dynamic nature. It bridges the past and the future, the explosive death of one star and the silent gestation of those yet to form. And just as its light continues to travel across space toward us, our gaze now turns deeper still to another remnant of cosmic upheaval, where radiation and time swirl into a silent cosmic whisper. As the Crab Nebula continues to expand across the quiet canvas of the Taurus constellation, its pulsar at the center reveals a deeper truth, one that transcends the remnants of supernovae and opens a doorway into a phenomenon that has reshaped our understanding of the universe. This rapidly spinning neutron star is not a solitary oddity, but a member of an extraordinary class of celestial objects that function as cosmic lighthouses. Pulsars, these enigmatic bodies, born from the death throes of massive stars, stand as some of the most exotic and precise timekeepers known to science. Their steady beat is not merely a rhythmic pulse, it is a gateway to exploring the extreme boundaries of physics, space-time, and the unseen structure of the cosmos. A pulsar is the ultra-dense, rapidly rotating core left behind after a supernova explosion. The explosion crushes a star's atoms into a sphere so dense that a single teaspoon of its material would weigh more than 1 billion tons on Earth. What remains is a neutron star, barely a dozen miles in diameter, spinning at mind-bending speeds, sometimes hundreds of rotations per second. Yet despite their compact size, pulsars emit powerful beams of electromagnetic radiation from their magnetic poles. As these beams sweep across the sky, like the rotating beams of a lighthouse, they produce regular flashes of energy detectable across vast distances. These pulses are so precise that some pulsars rival the accuracy of atomic clocks, ticking with unwavering constancy for millions of years. The discovery of pulsars in the late 1960s was not just a breakthrough, it was a revelation. British astrophysicist Jocelyn Bell Burnell, a graduate student at the time, noticed strange, regular radio signals emanating from deep space. At first, these repeating pulses were so unfamiliar that they were jokingly labelled LGM, short for Little Green Men, as scientists briefly considered the remote possibility of extraterrestrial origin. But further investigation soon revealed a natural, though no less astonishing, explanation. Pulsars were the collapsed cores of massive stars, spinning with intense magnetic fields and radiating energy in beams like cosmic metronomes. Pulsars are classified by their rotation rates and behaviors. Some rotate slowly, their beams pulsing every few seconds. Others, known as millisecond pulsars, spin hundreds of times each second, having been accelerated by matter from a companion star in a binary system. These ultra-fast pulsars are often found in ancient globular clusters, where dense stellar populations encourage interactions that spin up old neutron stars to blistering speeds. The very existence of millisecond pulsars challenged previous notions about the lifespan and evolution of neutron stars, revealing a process of recycling stellar remnants through complex gravitational partnerships. But pulsars are more than just strange remnants. They are powerful tools for science. Their regularity allows astronomers to map gravitational waves, test the limits of general relativity, and even search for ripples in space-time caused by the collisions of supermassive black holes. The pulsar timing arrays, a network of observatories spread across Earth, rely on the precise timing of pulsars to detect these elusive waves, opening new frontiers in astrophysics. These silent sentinels also aid in spacecraft navigation, functioning as natural GPS markers in deep space. NASA has even begun developing pulsar-based navigation systems for interplanetary missions, enabling autonomous spacecraft to calculate their positions far from Earth using nothing more than the rhythms of pulsars. Some pulsars behave unpredictably, producing sudden glitches, brief increases in rotational speed that reveal dynamic changes in their dense interiors. These glitches, possibly caused by shifts in the superfluid core of the neutron star, offer a rare glimpse into states of matter that cannot be replicated on Earth. Through them, scientists are studying quantum phenomena on a macroscopic scale, investigating the behavior of particles and forces under crushing pressures and mind-bending densities. Magnetars, an extreme subclass of pulsars, possess magnetic fields thousands of times stronger than typical neutron stars. Their magnetic energy is so immense that it can distort atomic structures and trigger violent outbursts of gamma radiation. These rare events have been detected even across galaxies and are believed to be linked to fast radio bursts, mysterious and short-lived radio pulses that continue to baffle astronomers. Each new discovery pushes the boundaries of human knowledge, challenging theories and demanding new models for understanding the universe. Yet pulsars are not merely scientific curiosities. They are cosmic storytellers. Their regular pulses carry with them echoes of ancient supernovae, the signatures of binary interactions, and the fingerprints of gravitational tides. Every beat they emit, every rotation they complete, marks a passage of time that outlasts civilizations. In their steady signals, we hear the rhythm of the cosmos itself, a beat that has remained unchanged across millennia. As we move deeper into the mechanisms that govern stellar death and rebirth, the pulsars guide our way with precision and clarity. But there is yet another layer to this story, one where stars explode not in silence, but in spectacular violence, bathing galaxies in bursts of gamma radiation so powerful they can momentarily outshine all the stars combined. From the pulsing hearts of dead stars, our journey now leads us into the most violent outbursts known in the cosmos, the gamma-ray bursts. Brief yet cataclysmic flashes that reveal the universe at its most extreme, following the tumultuous birth of the Crab Nebula, where a dying star etched its final breath across the cosmos in a display of unimaginable power. The universe did not fall silent. Instead, from the remains of such celestial cataclysms emerged one of the most intriguing and rhythmic phenomena ever discovered: pulsars. These rapidly rotating neutron stars are the lighthouses of the universe, flashing their beams of electromagnetic radiation in precisely timed intervals across the vast expanses of space. But behind their hypnotic pulses lies a story of crushing density, exotic physics, and cosmic clocks that challenge our understanding of time itself. When a massive star ends its life in a supernova, the remaining core may collapse into a neutron star, a celestial object so dense that a single teaspoon of its material would outweigh a mountain. In some cases, if the angular momentum of the progenitor star is preserved, this compact remnant begins to spin at staggering speeds, sometimes rotating dozens or even hundreds of times per second. It is in this furious spin, paired with a powerful magnetic field, that the secret of pulsars lies. These stars emit intense beams of radiation from their magnetic poles, and as the neutron star rotates, these beams sweep across space. If Earth happens to lie in the path of this sweeping beam, we observe a pulse of energy at precise, regular intervals, hence the name pulsar. First discovered in the late 1960s by Jocelyn Bell Burnell and Anthony Hewish, the initial signal was so regular that the team briefly considered the possibility of extraterrestrial origin. The signal pulsed with uncanny precision, like a cosmic heartbeat emanating from beyond our planet. This discovery sent shockwaves through the scientific community, opening up an entirely new realm of astrophysical study. Since then, pulsars have proven to be far more than curious remnants of stellar death. They have become indispensable tools in our quest to understand the universe. Some pulsars, known as millisecond pulsars, rotate hundreds of times per second with a precision that rivals the most accurate atomic clocks on Earth. These objects have become natural laboratories for the laws of physics under conditions impossible to replicate on our planet. Their extreme gravitational fields allow scientists to test Einstein's theory of general relativity in regimes far beyond our earthly reach. Moreover, when pulsars exist in binary systems, particularly those orbiting another neutron star or black hole, they allow astronomers to measure gravitational waves, subtle ripples in the fabric of space-time that were first predicted by Einstein over a century ago and only recently confirmed by observatories like LIGO. Pulsars also reveal the dynamic and interconnected nature of our universe. Some have been found flinging relativistic winds of charged particles into space, creating pulsar wind nebulae that glow with high-energy radiation. Others act as silent sentinels in the galactic landscape, maintaining their pulse for millions of years as they slowly lose rotational energy. And yet others have been known to suddenly shift their rotational speeds, a phenomenon called a glitch, offering rare insight into the inner structure of neutron stars, possibly even hinting at the presence of exotic forms of matter, such as quark gluon plasma or superfluid cores. The study of pulsars has also extended into the realm of practical cosmic navigation. Because their signals are so precise, astronomers have proposed using them as cosmic beacons for spacecraft, allowing for autonomous navigation far beyond the reach of Earth-based GPS systems. In fact, the Pioneer and Voyager spacecraft carried plaques and golden records with the position of Earth triangulated from known pulsars, an interstellar map should any distant intelligence ever come across them. Pulsars, then, are more than relics of stellar death. They are cosmic metronomes, gravitational probes, and celestial lighthouses. Their existence ties together the life cycles of stars, the theory of relativity, and the future of deep space exploration. Each pulse is a reminder that even in the aftermath of destruction, the universe gives rise to patterns of astonishing order and beauty. And as these cosmic clocks keep ticking, they guide our gaze even deeper into the tapestry of space, leading us toward phenomena even stranger still, such as magnetars, whose magnetic fury and sudden outbursts might hold the key to some of the universe's most powerful explosions and energy releases. As we leave behind the cosmic pulses of the spinning remnants known as pulsars, those enigmatic lighthouses of the universe, we begin to sense an even deeper mystery tugging at the very fabric of space. While pulsars spin with almost mechanical precision, echoing the death throes of massive stars, another force operates on a vastly grander scale, quietly but powerfully influencing the motion of entire galaxies. This force, invisible to the eye and difficult to define, is a gravitational mystery so immense that it bends the trajectories of hundreds of thousands of galaxies, including our own Milky Way. This phenomenon is called the Great Attractor. First discovered in the late 1970s, the Great Attractor did not announce its presence with light or motion, but through the unexpected behavior of galaxies. Astronomers noticed that our galaxy, along with its neighboring members in the local group and those in surrounding clusters such as Hydra and Centaurus, appeared to be streaming toward a specific region of space at staggering speeds. These galaxies were not merely drifting through the universe, they were accelerating en masse, as if being drawn by a colossal unseen hand. This curious movement, referred to as the peculiar velocity, deviated from what would be expected from the universe's expansion alone. Something massive and gravitationally dominant had to be causing this flow, but identifying the source proved to be no easy task. The region of space toward which this flow was directed lies behind the dense disk of our own Milky Way. This area is known as the zone of avoidance, where interstellar dust and stars obscure our view of the extragalactic sky. The cosmic curtain concealed whatever was lying beyond, and for decades, scientists were left to hypothesize what lay hidden. Was it a monstrous supercluster, a massive filament of dark matter, or was it something entirely different, something our tools had not yet evolved to detect? Eventually, with the help of infrared and radio telescopes able to pierce through the galactic veil, astronomers began to reveal clusters of galaxies previously unseen. Among these was the Norma cluster, a gravitational heavyweight of the cosmos, anchoring part of the flow in that mysterious direction. But the full mass responsible for the gravitational pull seemed to exceed what could be observed. The Great Attractor itself remained elusive. Not a single object or structure, but a gravitational center spread across hundreds of millions of light years, possibly encompassing several large clusters or feeding into a larger gravitational basin. What makes the Great Attractor even more fascinating is how it may be just one part of an even grander cosmic phenomenon. Over time, studies extended the scope of investigation and uncovered a far larger structure, the Laniakea supercluster, which includes the Milky Way, the Great Attractor, and many other galaxy clusters. In Hawaiian, Laniakea means immense heaven, a fitting name for a structure that spans over 500 million light-years and contains hundreds of thousands of galaxies. Within this titanic web of matter, gravity orchestrates the motion of galaxies like the flow of rivers down a basin, all converging toward gravitational valleys. The Great Attractor sits near one such valley, the deepest part of Laniakea's landscape, a gravitational confluence drawing galaxies inward like water down a cosmic drain. What lies at the heart of this attraction remains partly speculative. Some believe dark matter plays a major role, as this invisible substance outweighs normal matter by a factor of 5 to 1 in the universe. It cannot be seen, but its gravitational fingerprints are everywhere. Others suggest that even larger and more massive structures, like the Shapley supercluster, a vast concentration of galaxies far beyond the Great Attractor, could be contributing to the motion, extending the scale of cosmic flow beyond even what we once imagined. The Great Attractor, then, is not merely a destination in the universe. It is a puzzle wrapped in gravity, obscured by our vantage point, and tied deeply to the structure of the cosmos itself. It forces us to rethink the shape and fabric of the observable universe, revealing that galactic motion is not purely random, but guided by massive, unseen gravitational contours carved over billions of years. And yet, as vast and mysterious as the Great Attractor is, it leads us to an even stranger frontier, where gravity, light, and time all seem to unravel at the edge of understanding. For as we move beyond gravitational basins and dark matter filaments, we find ourselves face to face with one of the most haunting ideas in modern astronomy, the possibility of parallel universes and the shimmering frontier of the multiverse. What lies beyond the observable boundary of our cosmos? Is our universe just one bubble in an infinite sea? And so we now turn toward that next extraordinary idea, the multiverse hypothesis, a concept that challenges not only our instruments and mathematics, but our deepest assumptions about reality itself. Long before our Milky Way found its place in the tapestry of cosmic time, the universe was ruled by blazing beacons that outshone entire galaxies. These ancient giants, known as quasars, were among the first lighthouses of the early cosmos, unfathomably distant, extraordinarily bright, and profoundly mysterious. To observe a quasar is to peer billions of years into the past, to a time when galaxies were still young, chaotic, and feverishly active. Each quasar is powered by a supermassive black hole at the heart of a galaxy, devouring matter at such a ferocious rate that the surrounding material becomes incandescent, releasing more energy than 1,000 galaxies combined. Their brilliance is not due to the black hole itself, which remains forever cloaked in darkness, but from the swirling maelstrom of gas and dust spiraling around it in the accretion disk. As this matter accelerates and heats up under the intense gravity, it emits radiation across the electromagnetic spectrum, radio waves, visible light, X-rays, and even gamma rays, turning these ancient engines into cosmic sirens that still echo across the universe. The discovery of quasars in the early 20th century was nothing short of a paradigm shift. In the early 1960s, astronomers first identified these puzzling objects as quasi-stellar radio sources, hence the term quasar. They looked like stars in early telescopes, but produced radio emissions far too intense to match any known stellar body. As observational technology improved, Scientists realized these objects were not just stars, but incredibly remote galactic cores, so far away that their light had traveled for billions of years to reach Earth. That light, dimmed by unimaginable distance, yet still piercing through time, told the story of a young, energetic universe. The most distant quasars known today formed just a few 100 million years after the Big Bang, offering rare glimpses into the universe's adolescence and the dawn of galactic formation. What makes quasars truly extraordinary is the scale and violence of the energy they unleash. Their central black holes can weigh millions to tens of billions of times more than our Sun, and yet they manage to manipulate their surroundings with an elegance that fuels cosmic evolution. The jets emitted from some quasars, beams of charged particles traveling at nearly the speed of light, can extend across intergalactic space, influencing star formation in neighboring galaxies and helping to distribute elements like carbon and iron across the cosmos. In this way, quasars are not merely markers of ancient activity, they are agents of change, sculptors of galactic architecture, and distributors of the very elements that make life possible. Even today, quasars continue to defy expectations. While they are most often associated with the distant past, a few active galactic nuclei, less luminous but similarly structured, still operate within our cosmic neighborhood. Studying these contemporary analogues allows astronomers to decode the mechanics of galactic nuclei without the filter of time and distance. Furthermore, quasars serve as crucial tools for measuring vast cosmic distances. Their brightness and predictability allow them to act as cosmic yardsticks, anchoring our understanding of the expanding universe and the elusive nature of dark energy. The tale of quasars naturally extends into the broader narrative of galactic transformation, and as we follow their trail of energy and light, we begin to see a connection to another marvel of cosmic evolution: galactic collisions. Just as quasars mark the turbulent birth of galaxies, the merging of galaxies marks a new chapter in their lives. The next stage in our journey takes us deep into the dance of titanic forces, where entire galaxies spiral toward one another, collide, and are reborn in brilliant explosions of stars and dust. Let us now explore the spectacular drama of galactic mergers. As galaxies collide and reshape one another across the ages, birthing waves of new stars in the turbulence of their union, there exist quieter but no less powerful cradles of cosmic creation. Regions where stars are not born from cataclysm, but emerge from the silent, methodical accumulation of dust and gas. Among these stellar nurseries lies one of the most breathtaking and iconic sights ever captured by human instruments: the Pillars of Creation. Imaged by the Hubble Space Telescope in the mid-1990s, this towering structure within the Eagle Nebula has become a visual emblem of the universe's raw power and delicate artistry. Three vast columns of cold, molecular hydrogen and interstellar dust stretch into space like fingers of creation, each one sculpted by radiation from nearby young stars. These are not lifeless towers. Within their shadows, new stars are forming in secret, hidden from view by thick veils of matter that shield them from the harsh ultraviolet light of nearby supernovae and stellar winds. What makes the Pillars of Creation so evocative is not merely their beauty, but their symbolism. They stand at the intersection of destruction and birth, constantly eroded by radiation even as they serve as incubators for new stars. At their tips are dense knots of gas, known as evaporating gaseous globules, regions so compact that they resist the forces tearing the rest of the pillars apart. These are the seeds of future stars. Under immense gravitational pressure, the gas within these globules begins to collapse, heating up and eventually igniting nuclear fusion at their cores. Each newly formed star, in turn, contributes to the ongoing transformation of its environment, blasting radiation outward and reshaping the very clouds from which it emerged. This feedback loop of creation and destruction is one of the most fundamental processes in astrophysics, echoing throughout galaxies across the observable universe. The pillars of creation are estimated to be several light years tall, so vast that even light traveling at over 600 million miles per hour would take years to traverse their length. Yet in the grand scope of space and time, these towers are ephemeral. Astronomers believe that the original structures may have already been destroyed by a supernova that occurred thousands of years ago, with its shockwave only now reaching us in real time. Because the Eagle Nebula lies more than 6,000 light-years away, what we see in the famous Hubble image is already ancient history, an echo of a structure that may no longer exist. This paradox of time and distance gives the pillars their haunting poignancy. We are witnessing the past, marveling at a moment in cosmic history that may have long since passed, preserved only in the frozen light that continues its journey toward Earth. Despite their ephemeral nature, the pillars of creation offer astronomers an invaluable laboratory for studying the early stages of star formation. Through the use of infrared observations, particularly from the James Webb Space Telescope, we are now able to peer into the dust-laden interiors of these columns and witness the very moment when gas clouds collapse to form protostars. These new eyes on the cosmos allow scientists to trace the life cycle of stars from their embryonic beginnings to their main sequence maturity. Such studies not only deepen our understanding of stellar physics, but also help explain the origins of planets, solar systems, and potentially life itself. The same processes taking place within the Eagle Nebula occurred billions of years ago in the molecular cloud that gave rise to our own Sun and Earth. In this sense, the pillars of creation are not merely remote phenomena. They are mirrors of our own origins. From the brilliant chaos of quasars to the fragile towers of star-birthing gas, the cosmos reveals itself in infinite forms and epochs. Each one tells a different chapter of the same eternal story, a universe in motion, forever shaping and reshaping itself. As we turn now from these stellar nurseries, glowing softly within our own galaxy, we cast our gaze once more into the far reaches of space, toward phenomena even more enigmatic and extreme. Ahead lies the vast and invisible realm of dark matter, a force that neither emits nor reflects light, yet binds galaxies together in a gravitational web whose patterns define the very structure of the universe. From the cosmic cradle of the pillars of creation, we shift our gaze outward, sweeping across interstellar gulfs, until we arrive at a magnificent structure, one that both enchants with its elegance and provokes deep scientific inquiry. This is NGC 1300, a majestic barred spiral galaxy, poised like a celestial whirlpool in the vast expanse of the Eridanus constellation. Situated over 60 million light-years from Earth, NGC 1300 is a sprawling masterpiece of gravitational architecture, a galaxy that challenges and refines our understanding of how stellar systems evolve and organize themselves over cosmic timescales. At first glance, NGC 1300 bears the classic shape of a grand design spiral galaxy, with arms unfurling gracefully from a bright centralized bar, a luminous spine of stars, gas and dust that stretches across the galaxy's core. Unlike unbarred spirals, which possess a central bulge from which arms extend, barred spiral galaxies like NGC 1300 exhibit a linear structure that appears to funnel matter inward, possibly fueling star formation and central black hole activity. The bar is not a static feature, but a dynamic phenomenon shaped by the rotational mechanics of the galaxy and the gravitational interplay of its contents. As such, NGC 1300 offers a valuable glimpse into the internal forces that shape galactic evolution. The sweeping spiral arms of NGC 1300 are not mere aesthetic flourishes, they are zones of intense astrophysical activity. These arms serve as stellar nurseries where interstellar gas collapses under its own gravity to form new stars. Embedded within these arms are clusters of young blue stars, brilliant beacons of recent stellar birth, surrounded by regions glowing with the faint red hue of ionized hydrogen. The pattern of star formation in NGC 1300 reveals the rhythmic, wave-like nature of spiral density waves, gravitational perturbations that move through the galactic disk, compressing gas and triggering star birth along the way. This intricate mechanism gives spiral galaxies their iconic structure and sustained vitality. Yet perhaps the most tantalizing feature of NGC 1300 lies at its very heart. Unlike many galaxies of similar scale, it shows no evidence of a luminous active galactic nucleus, the bright and violent signature of a supermassive black hole devouring matter at high velocity. Instead, its core appears relatively quiescent, a surprising anomaly that poses questions about the life cycles of galactic centers. Observations from the Hubble Space Telescope have revealed a striking mini-spiral structure within the nucleus itself, suggesting that while NGC 1300's black hole may currently be dormant, it still exerts a gravitational influence on the surrounding gas and stars. This inner structure echoes the architecture of the galaxy at large, as though mirroring its cosmic form on a smaller central scale. NGC 1300 has also proven vital in understanding the broader evolutionary context of galaxies. Its classification as a barred spiral contributes to ongoing research into the frequency and function of galactic bars across the universe. Astronomers believe that as galaxies age, many develop bar structures as part of their natural dynamical evolution. These bars may act as conduits, channeling gas from the outer regions toward the center, thereby igniting new phases of star formation or black hole growth. Thus, barred spirals like NGC 1300 serve as both laboratories and time capsules, embodying processes that may unfold over billions of years. Even in its relative stillness, NGC 1300 offers a wealth of insights into cosmic structure and transformation. It stands as a pristine example of gravitational balance, star-forming vigor, and internal symmetry. Observing it is like watching a galactic ballet, an interplay of matter, energy, and time, choreographed by the fundamental laws of physics. But the beauty and precision of NGC 1300 also prepare us for the chaotic vastness beyond it. As we continue our journey, we begin to encounter the forces that defy the elegance of symmetry. The colossal collisions of galactic titans, the violent mergers that sculpt new galaxies from the remnants of others. These interactions, far from being rare events, have shaped much of the universe we see today. The next phase of our cosmic odyssey takes us into the realm of colliding galaxies, where gravity becomes a disruptive artist and the canvas of the cosmos is rewritten with every impact. Tidal galaxies. Twisted by gravity. In the grand cosmic ballet, not all galaxies retain their serene, symmetrical shapes. Some are sculpted by chaos, stretched, warped, and reshaped by the irresistible hand of gravity. These are tidal galaxies, distorted, twisted structures born from powerful gravitational encounters. Their haunting shapes are evidence of galactic interactions on a colossal scale, revealing a hidden layer of violence in the universe's evolution. Unlike solitary spiral or elliptical galaxies, tidal galaxies are forged in the heat of close encounters, where entire systems of stars, dust, gas, and dark matter are flung apart or pulled inward, reshaped by the mutual gravitational forces of colliding giants. The universe is far from static, and these distorted structures are the fossilized footprints of its most turbulent episodes. The term tidal is not a poetic flourish, but a scientific truth. Just as Earth's oceans rise and fall under the gravitational pull of the Moon, galaxies too experience tidal forces when they pass near or collide with one another. These forces stretch and shear the galaxies apart, creating sweeping tails, luminous bridges, and elaborate arcs of matter that arc through space like cosmic brushstrokes. In some instances, entire arms are pulled from spiral galaxies, forming structures that glow with new star formation. The Antennae galaxies and the Mice galaxies are stunning real-world examples, frozen in time during their dramatic transformations. These galactic duets are not brief. Their interactions may take hundreds of millions of years to unfold, with the final result often being the fusion of the galaxies into a single new entity. Tidal galaxies are not just visual marvels, they offer a unique laboratory for studying galactic dynamics, star formation, and the invisible architecture of dark matter. When galaxies interact, their gas clouds are compressed, sparking intense waves of star formation. These newborn stars often illuminate the tidal features, giving them their ghostly glow. In the chaos of these interactions, astronomers can measure how gas and dust respond to gravitational torques, how star clusters form and disperse, and how the core of a galaxy might be fed with material that wakes up its central black hole. These tidal remnants expose the otherwise invisible framework of dark matter halos that extend far beyond the visible parts of galaxies, bending and shaping their behavior. They are natural experiments, revealing secrets that cannot be replicated in any laboratory on Earth. But not all tidal features arise from direct collisions. Some are the result of flybys, near misses that disturb a galaxy without fully merging with it. Others involve dwarf galaxies being torn apart by their larger hosts, unraveling into stellar streams that snake across the sky. The Milky Way itself is surrounded by these stellar fossils, the remnants of smaller galaxies it has devoured over time. The Sagittarius stream is one such remnant, wrapping around our galaxy in a vast tidal loop. These streams whisper tales of past violence and cannibalism, suggesting that galaxies grow not just through birth, but through consumption and transformation. Observations using the Hubble Space Telescope and powerful ground-based observatories have allowed astronomers to trace these faint, delicate structures in exquisite detail. In many cases, they can reconstruct the history of an encounter, pinpointing when the galaxies met, how close they passed, and what tidal forces shaped their current appearance. Computer simulations add another layer of understanding. allowing scientists to rewind or fast-forward cosmic collisions, predicting how current interactions might evolve over the next billion years. These visualizations are not speculative, they are grounded in hard physics and guided by observational data. They bring to life the hidden drama unfolding across intergalactic distances. Tidal galaxies also hold profound implications for the future of our own Milky Way. The Andromeda Galaxy, our nearest spiral neighbor, is on a slow magmation collision course with us. In about 4 billion years, the two will merge in a titanic event that will likely produce a tidal galaxy of epic proportions. As their stars swirl and stretch through one another, vast tails of stars will sweep into intergalactic space, while the cores spiral together and settle into a new, larger elliptical galaxy. Earth itself may survive, but the night sky will be transformed into a kaleidoscope of stellar chaos. By studying existing tidal galaxies today, astronomers are essentially looking at previews of our galaxy's far future. These warped, winding structures are not rare outliers, but essential pieces in the puzzle of cosmic evolution. Galaxies are social entities, and their interactions have shaped the structure of the universe as we know it. Tidal galaxies are living records of those interactions, etched into space by gravity's unyielding hand. They are snapshots of creation through destruction, of growth through disruption. In their luminous arcs and twisted spirals, they reveal that beauty in the cosmos is often born from collision, chaos, and the relentless pull of gravity. As we follow these cosmic strands of connection and distortion, we arrive at a deeper understanding of the transformative power of galactic encounters. But beyond these twisted beacons lie even more enigmatic structures, rings that form not from collapse or collisions alone, but from a different kind of dynamic interplay. These are the ring galaxies, whose symmetry seems almost unnatural in a universe ruled by turbulence and entropy. To understand their origin is to uncover another layer of galactic mystery. Tidal galaxies, twisted by gravity. In the vast, cold architecture of the universe, galaxies are not the isolated islands we once believed them to be. They are wanderers in a sea of gravitational tides, drawn toward one another in slow, majestic dances that can last for billions of years. These cosmic encounters leave behind breathtaking relics, tidal galaxies contorted and stretched by the overwhelming force of gravity. These galactic forms are not merely visual spectacles. They are deep records of the universe's dynamism, violence, and continuous creation. Tidal galaxies emerge from gravitational interactions between massive galaxies. Unlike the serene spirals we often imagine when thinking of galaxies, tidal galaxies wear the scars of cosmic battles. When two or more galaxies come close enough, their mutual gravitational pull begins to tug at their outer stars, clouds of gas and dark matter. These tugs do not happen instantly, but unfold over millions or even billions of years. Stars are flung into tidal tails, enormous, thread-like streams of stellar material, stretching across intergalactic space, sometimes forming arcs that span hundreds of thousands of light-years. The first clues to the existence of tidal galaxies came in the mid-20th century with improvements in photographic plate sensitivity and telescope optics. Astronomers began noticing peculiar galaxy shapes, twisted, stretched, and bent structures that defied classical spiral or elliptical categorization. The classic pair, known as the antennae galaxies, is one of the most iconic examples. Located in the constellation Corvus, this duo appears to be locked in a slow magmatic collision, their stars flung outward in brilliant arcs that resemble insect antennae. These trails are not static. They evolve, merge, and sometimes collapse into new structures altogether. But the wonder of tidal galaxies lies not only in their forms, but in what they teach us about galactic evolution. These interactions often trigger immense waves of star formation. As gas clouds are compressed by gravitational forces and shock waves, they collapse under their own weight, igniting bursts of newborn stars. Some of the most vibrant stellar nurseries ever observed are found in the heart of tidal interactions. Yet this creation often comes with destruction. Galactic cores may be destabilized. Supermassive black holes can begin to consume more matter, and entire structural features of galaxies may be torn apart, never to reform. From a scientific perspective, tidal galaxies offer an exceptional opportunity to study the role of gravity not just as a force of attraction, but as an agent of transformation. Simulations and models of galaxy collisions have revealed that these events are not rare. In fact, the Milky Way itself is not immune. Our home galaxy is on a collision course with the Andromeda Galaxy, a celestial ballet expected to begin in earnest in about 4 billion years. Already, satellite galaxies like the Large and Small Magellanic Clouds are stirring up tidal features in the Milky Way's halo, subtle arcs of stars and gas that hint at the beginning of a grand merger. These future tidal features will reshape the Milky Way, giving rise to yet another generation of twisted, luminous structures. Even the dark matter component of galaxies plays a crucial role in shaping tidal galaxies. Though invisible, dark matter contributes the majority of mass in most galaxies, forming vast halos that extend far beyond the visible stars. During a galactic encounter, these dark matter halos interact gravitationally as well, guiding the overall shape and trajectory of the tidal structures. Without dark matter, tidal interactions would look radically different, less organized, less elongated, and lacking the coherence we observe. Thus, tidal galaxies serve as a silent testimony to the dark scaffolding of the universe. Beyond their scientific importance, tidal galaxies also carry philosophical weight. They remind us that beauty often comes from struggle, and that creation is frequently born from conflict. They are visual metaphors for resilience and transformation, telling a story of cosmic resilience and rebirth. Through their tortured shapes, we see the universe not as a static machine, but as a living, evolving organism, one that tears itself apart and builds anew, cycle after cycle. Yet even these grand tidal features are temporary. Over vast stretches of time, the dramatic tails and bridges will fade, stars will disperse into the larger galactic halos, and the memory of the collision will be lost, save for the newly merged galaxy at its center. These tidal ghosts are fleeting moments in the infinite film of cosmic evolution, captured only briefly by human eyes and instruments before they vanish into the background of space. As we observe these twisting galactic forms, we are not only looking outward, but forward. They are glimpses into the eventual fate of all galaxies, including our own. In their chaotic grace, tidal galaxies are both messengers of history and harbingers of what is to come. And with that glance into future galactic collisions and their inevitable consequences, we turn our attention to a stranger cosmic choreography, one that transcends even the most dramatic galaxy mergers. Next, we step into the realm of Outline 12, where we explore the bizarre and captivating world of ring galaxies, formed not by gradual spiral evolution, but by violent head-on collisions that send ripples through galactic disks like stones cast into a still. The Hercules Corona Borealis, Great Wall, the largest structure in the universe. As we leave behind the intricate gravitational dances that twist galaxies into tidal forms, our perspective must widen, not just across space, but across the very concept of scale itself. From the delicate, luminous threads spun by merging galaxies, we now move into a realm so vast, so profoundly immense, that it challenges the very boundaries of human comprehension. We arrive at what may be the largest known structure in the observable universe, the Hercules Corona Borealis Great Wall, a name as colossal as the cosmic giant it represents. Discovered in the early years of the 21st century, this immense superstructure came into view not through visible light or classical imaging, but through the detection of gamma-ray bursts, brief, high-energy flashes of radiation that typically signal the collapse of massive stars or the violent mergers of neutron stars. Astronomers analyzing data from deep sky surveys noticed a peculiar concentration of these bursts in a specific region of the sky, a statistical clustering too significant to be coincidental. The distribution pointed to a massive assembly of galaxies and galaxy clusters stretching across a truly unimaginable expanse, billions of light-years in length. The Hercules Corona Borealis Great Wall spans a region of sky that connects the constellations of Hercules and Corona Borealis, hence its name. The dimensions of this structure are staggering, over 10 billion light-years across at its greatest extent. To put this in context, our entire Milky Way galaxy is roughly 100,000 light-years in diameter. The Great Wall dwarfs not only our galaxy, but entire supercluster of galaxies, swallowing them like islands in a galactic ocean. It is not a wall in the traditional sense, but rather a vast web of gravitationally associated matter. Galaxies, dark matter, intergalactic gas, all interconnected in a filamentary structure that traces the skeleton of the cosmos. This raises a profound problem. According to the cosmological principle, the foundational idea in modern astrophysics that the universe is homogeneous and isotropic at sufficiently large scales, structures larger than about 1 billion light-years should not exist. The Hercules Corona Borealis Great Wall breaks that rule. It defies the expected limits of cosmic structure formation, posing a direct challenge to prevailing models of the early universe and the evolution of large-scale structure. If such a massive complex exists, how did it form within the age of the universe, and what unknown mechanisms might have guided its growth? Some scientists suggest that the wall could be a projection effect. Is more efficient across cosmic timescales than previously thought. This structure is part of a broader cosmic web, a vast interconnected lattice of filaments, voids, and nodes that define the very texture of the universe. Galaxies are not sprinkled evenly across space. Instead, they are found in thread-like formations, with vast empty regions in between. These threads converge in knots known as galaxy clusters, and the clusters themselves connect into larger assemblies called superclusters. The Great Wall may be the most extreme example of this arrangement, a kind of cosmic superhighway, where gravity has drawn together matter over distances that stagger the imagination. But the Great Wall is not just about scale. It also forces us to confront questions about the nature of the universe itself. If our cosmological assumptions are incorrect, what else might we be missing? Could there be even larger structures beyond our observational horizon? Or is the universe not as uniform as we once believed? The possibility that the cosmos harbors such immense, coherent formations adds fuel to discussions about anisotropies in the cosmic microwave background, alternative models of inflation, and even multiverse theories. Moreover, the Hercules Corona Borealis Great Wall reveals the extraordinary power of invisible forces in shaping the visible universe. Dark matter, unseen but gravitationally dominant, likely forms the backbone of this superstructure. Though we cannot see it directly, its influence is everywhere, guiding the motion of galaxies and sculpting the very architecture of space. In this way, the Great Wall becomes not only a structure of light and matter, but also a monument to the unseen, a cosmic fingerprint left by forces we still struggle to define. Even our ability to detect such a structure is a triumph of human ingenuity. The technology required to observe gamma-ray bursts across billions of light-years, to map their distribution, and to infer the existence of such a structure is itself the result of generations of scientific progress. From orbiting observatories to global data-sharing networks, the discovery of the Great Wall is a testament to how far humanity has reached into the deep night of space. And yet, as vast as it is, the Hercules Corona Borealis Great Wall may not be the final frontier of cosmic structure. As our instruments improve and our theories evolve, we may discover other megastructures, richer webs, longer filaments, deeper voids, stretching across space like neural pathways in a cosmic mind. And that idea, strange and poetic as it sounds, leads us to our next domain of wonder. For if the large-scale structure of the universe resembles a neural network, if it operates like an interconnected web, then it invites an even more profound question. Could the universe itself be conscious? Or does it possess some deeper logic that echoes the patterns of thought, memory, and awareness? As we journey forward into Outline 13, we shall confront the enigmatic frontier of cosmic consciousness, where physics meets philosophy, and where science begins to question the nature of perception, sentience, and the very architecture of reality itself. Starburst galaxies, galaxies on fire. From the colossal stillness of the Hercules Corona Borealis Great Wall, where cosmic architecture unfolds on a scale that mocks our sense of proportion, we now plunge back into more intimate, but no less dramatic, arenas of galactic life. If the Great Wall revealed the structure of the universe in skeletal form, then starburst galaxies represent its beating heart. Galaxies in a phase of violent, feverish transformation, igniting stars at a rate so furious that their entire evolutionary trajectory is altered. These are galaxies on fire, not with literal flames, but with the incandescent heat of explosive creation. A starburst galaxy is a galaxy caught in the throes of intense star formation, producing new stars at rates that can be dozens or even hundreds of times higher than those of ordinary galaxies. This frenzy of stellar birth is not a steady process, but a dramatic episode, a relatively short-lived surge in activity, often triggered by a specific catalyst. In astronomical terms, these starbursts are brief flashes of light and energy, often lasting only tens of millions of years, a blink of time compared to a galaxy's total lifespan, which typically stretches across billions of years. The triggers for starburst phases are as varied as they are violent. Galactic collisions, tidal interactions, and even internal gravitational instabilities can funnel vast quantities of cold gas into the central regions of a galaxy, collapsing it under its own weight. When this gas compresses rapidly, it creates the perfect conditions for star formation on a massive scale. Shock waves from previous supernovae, spiral density waves, or the gravitational tug of a passing satellite galaxy can all act as catalysts. The result is a firestorm of stellar birth, an astronomical version of a population explosion, where thousands of stars are born every year in tightly packed regions. One of the most studied starburst galaxies is Messier 82, also known as the Cigar Galaxy. Located in the constellation Ursa Major, it has become a cosmic laboratory for understanding the mechanics of starbursts. At its core, Messier 82 churns out stars at such an accelerated pace that its central regions glow with radiation, wind, and heat. Observations have revealed superwinds, enormous outflows of gas, driven by the combined energy of young stars, stellar winds, and supernovae blasting material out into intergalactic space. These superwinds can stretch for tens of thousands of light years, carrying not just gas but also heavy elements forged in the hearts of stars. The consequences of a starburst are profound and far-reaching. First, the sheer number of new stars changes the galaxy's structure and composition. Massive stars, which burn quickly and die young, explode as supernovae, enriching the surrounding space with metals like iron, calcium, and oxygen. These elements are essential for the formation of planets, moons, and life as we know it. In a sense, starburst galaxies are not only creating stars, but also seeding the future building blocks of life across the cosmos. Second, the energy released during a starburst can alter the galaxy's future. The supernovae and stellar winds inject so much momentum into the surrounding gas that it can halt further star formation or even eject gas entirely from the galaxy. This process, known as feedback, creates a self-regulating mechanism. A galaxy can only sustain a starburst for so long before it depletes its gas reserves or blows them out into space. Thus, the same process that ignites star birth can also extinguish it, leaving behind a quieter, more stable system. Or sometimes a galaxy stripped of its fuel, unable to form stars for eons. There is also a deeper cosmological importance to these luminous bursts of creation. Starburst galaxies are more common in the early universe, where galaxy interactions and mergers were frequent. Studying them allows astronomers to peer backward in time, understanding how the first galaxies evolved, how heavy elements were distributed, and how large-scale structures formed. Starbursts may even be connected to the emergence of quasars, those brilliantly bright, black hole-powered beacons that shine across the deep past. In some cases, the same galactic collisions that trigger a starburst also feed the central black hole, setting off a chain reaction of cosmic activity that transforms the galaxy entirely. And beyond science, there is something undeniably poetic about starburst galaxies. They are the very embodiment of cosmic urgency, a blaze of life in the cold darkness of space. They speak to us about energy, transformation, and the delicate balance between growth and destruction. In their glowing cores and radiating winds, they offer a glimpse of the universe at its most active and alive, showing us that galaxies are not static ornaments, but dynamic entities shaped by pressure, momentum, and the relentless pulse of birth and death. Even their infrared and radio signatures tell a story. Much of their activity is obscured by dust, hidden from visible light, but revealed in other wavelengths. This makes starburst galaxies prime targets for observatories like the James Webb Space Telescope, which can peer into these dust-shrouded regions to reveal the tangled dance of stars being born amid clouds of gas. In doing so, we not only witness the inner workings of starburst galaxies, but also refine our understanding of stellar life cycles, galactic evolution, and the chemical heritage of the universe itself. And as we leave behind these luminous furnaces of creation, we are once again drawn toward mystery, toward that other side of galactic behavior that does not involve bursts of activity, but rather silence, decay, and disappearance. The universe, in all its grandeur, is not only a place of expansion and birth, it is also home to fading light, to celestial phenomena that whisper of ends rather than beginnings. And so, as we transition forward, we enter the domain of Outline 14, where we will explore the enigmatic nature of dark galaxies, galaxies without stars, invisible to ordinary observation, yet teeming with dark matter and hidden potential, veiled in the silence of the cosmic void, intergalactic stars, the loneliest wanderers in the cosmos. As we depart the heart of starburst galaxies, those luminous engines of creation, we are drawn toward a far more solitary and silent region of the universe. It is a realm not defined by frenetic birth or gravitational clashes, but by isolation, motion, and mystery. Here, between the vast gulfs that separate galaxies, travel stars that belong to no stellar city, no spiral arm, no galactic nucleus, these are the intergalactic stars, often called rogue stars, celestial exiles drifting through the dark vacuum between galaxies, untethered and alone. To understand the profound nature of these wandering stars, we must first grasp the environment they inhabit. The space between galaxies, known as the intergalactic medium, is vast and almost unimaginably empty. In these regions, the density of matter is so low that even light takes millions of years to travel between recognizable landmarks. Yet, scattered across this cosmic void are stars that shine, burn, and age like their galactic cousins. But with one critical difference: they do so in isolation. The existence of intergalactic stars was first proposed as a theoretical consequence of galactic interactions. When two galaxies collide or pass closely by one another, the powerful gravitational forces involved can fling stars out of their home systems. These ejected stars are accelerated to such high velocities that they escaped the gravitational pull of both galaxies, hurtling outward into the intergalactic abyss. This process is not random chaos. It is governed by the elegant laws of orbital mechanics and the conservation of momentum. The most common mechanism involves gravitational slingshots, where stars near the core of a merging system are caught in the complex ballet of colliding tidal forces and flung outward with enough energy to break free from their galaxy's embrace. Observational confirmation came slowly, due in large part to the difficulty of detecting stars in deep space without the background glow of a galaxy. But with the advancement of deep-field telescopes and instruments sensitive to faint light sources, astronomers began to identify luminous points floating between galaxies in clusters like Virgo and Coma. These stars, many of them red giants and supergiants, were too far from any galaxy to be bound to one, and their spatial distribution made clear that they were not mere statistical outliers. Instead, they represented a population of stars that had been torn from their homes and scattered across the intergalactic medium. The implications of these stars extend far beyond their unusual positions. Intergalactic stars act as tracers, natural probes that help map the gravitational and structural dynamics of galaxy clusters. Their distribution can reveal the history of past mergers, the mass distribution of dark matter halos, and the violent processes that have shaped the architecture of the universe. They are, in a sense, the fossils of cosmic violence, silent witnesses to events that unfolded over billions of years. Moreover, these stars challenge our understanding of stellar evolution in isolated environments. Most stars live within galaxies, where interstellar gas, magnetic fields, and stellar neighbors influence their formation, movement, and eventual death. But intergalactic stars exist largely without these interactions. They are solitary in the truest sense, evolving without the feedback mechanisms that govern galactic stellar populations. This isolation could lead to subtle differences in their lifespans, rotation rates, or end-of-life behavior, differences that are still being studied and debated by astrophysicists. Some of these rogue stars are hypervelocity stars, traveling at speeds so extreme that they were likely ejected not just by merging galaxies, but by interactions with supermassive black holes. When a binary star system strays too close to such a black hole, tidal forces can rip it apart, flinging one star into intergalactic space while the other is devoured. These events produce some of the fastest objects in the universe and demonstrate the raw, destructive power of galactic core. Even more intriguing is the possibility that some intergalactic stars carry with them planetary systems, entire solar systems cast adrift in the cold dark. These potential rogue planets, orbiting stars far from any galaxy, might harbor moons, atmospheres, or even the elemental ingredients of life, all while flying through a universe that offers no nearby suns, no galactic context, and no celestial neighborhood. While purely speculative for now, the existence of such orphaned worlds poses deep philosophical questions about life's resilience and its possible emergence in environments we have barely begun to understand. Intergalactic stars also hint at the broader fate of galaxies and cosmic evolution. As galaxies merge and evolve, as stars are ejected and redistributed, the boundaries between what we call a galaxy and what lies outside it become blurred. Over cosmic timescales, stars leaking from galactic halos could form vast intergalactic stellar bridges, or clouds, challenging our definitions of structure and membership in the universe. The line between galaxy and intergalactic space is more porous than once believed. These lonely travelers, though few compared to the vast populations housed within galaxies, carry with them the stories of upheaval, acceleration, and exile. They shine against a backdrop of emptiness, reminding us that even in the most desolate reaches of space, stars still burn, life still pulses, and history continues to unfold. They offer us a unique lens, one not centered on belonging, but on freedom, motion, and the far-flung consequences of cosmic evolution. And just as these solitary stars illuminate the darkness between galaxies, they guide us toward another elusive phenomenon that inhabits the threshold of the observable and the theoretical. As we follow their trail further into the cosmos, we encounter not visible stars or known matter, but something far more mysterious and paradoxical: galactic systems that seem to contain no stars at all. In Outline 15, we delve into the strange, silent world of dark galaxies, invisible structures of hydrogen and dark matter that defy direct observation, yet may hold the keys to understanding how galaxies form, how matter assembles, and how much of the universe remains unseen. Dark galaxies, the invisible engines of the cosmos, as the glowing exiles of space. The intergalactic stars drift through the cosmic void in solitude. They reveal the aftermath of galactic upheaval and the dynamic violence that can unbind a star from its origin. But now we turn toward a stranger silence, not the quiet of isolation, but the absence of light itself. We descend into the shadows of the universe, seeking entities so elusive they cannot be seen. Yet their gravitational fingerprints mark their presence. These are the dark galaxies, structures composed almost entirely of invisible matter and gas, nearly devoid of stars and nearly undetectable by conventional observation. They are the missing pieces in our cosmic puzzle, the phantom frameworks on which the luminous universe is built. The notion of a galaxy without stars seems almost contradictory. For centuries, our understanding of galaxies was built around their stellar components. Grand spirals of burning suns, ellipticals crowded with ancient stars, irregulars alive with star-forming clouds. Yet, as astronomical techniques improved and our surveys deepened, anomalies began to surface. Astronomers observed gravitational lensing where there should have been no visible mass. Hydrogen gas clouds swirled and rotated as though held together by unseen hands. These spectral structures hinted at massive collections of matter behaving like galaxies, but radiating little or no visible light. Thus emerged the theory of dark galaxies. Galaxies that possess the gravitational architecture of ordinary systems, but remain cloaked in obscurity. The primary signature of these entities lies in their hydrogen content. Neutral hydrogen emits radio waves at a specific wavelength, a spectral fingerprint that allows radio telescopes to detect and map vast clouds of interstellar gas. In regions where no stars are visible, but where this 21-centimeter line is strong and coherent, astronomers infer the presence of gas-rich galaxies that have failed to ignite into light. They rotate like galaxies, move like galaxies, and interact with other cosmic structures as galaxies do. Yet they shine with almost no visible light. These are the dark galaxies, whispering their existence through the quiet hum of hydrogen. One of the most compelling candidates for a dark galaxy is Virgo He 21, a hydrogen-rich cloud located in the Virgo cluster. This object exhibits a strong rotational signature, implying a massive gravitational source. Yet deep optical surveys reveal no stars. Its motion and mass distribution suggest it is bound by an extensive dark matter halo, providing the gravitational cohesion necessary to keep it intact. It is not simply a fragment or remnant. It behaves like a galaxy, just one in which star formation has been suppressed or never initiated. This brings us to the deeper mystery. Why would a galaxy fail to form stars? The process of star formation depends on the cooling and collapse of gas within a gravitational well. But if the gas remains too warm, too diffuse, or too turbulent, it cannot contract into dense stellar cores. Feedback mechanisms from nearby galaxies, cosmic reionization in the early universe, or even internal gravitational instability could prevent star formation from taking hold. In this scenario, the dark galaxy becomes a kind of frozen potential, a massive reservoir of raw material that never crosses the threshold into illumination. Dark galaxies may be more than rare oddities. They could play a foundational role in galaxy formation itself. According to simulations of the early universe, galaxies formed through hierarchical assembly. Smaller structures merge to form larger ones, building complexity over time. Many of the earliest building blocks may have been dark or nearly dark, aggregating gas and dark matter before conditions became right for star formation. In this sense, modern dark galaxies may be evolutionary holdouts, primordial remnants from an earlier cosmic era caught in suspended development. Moreover, these elusive structures challenge our methods of cosmic census. The luminous universe, the stars, the galaxies, the glowing nebulae, is only a partial map. If dark galaxies are numerous, then we may be drastically underestimating the number and distribution of galactic systems. Their presence may explain discrepancies in mass calculations for galaxy clusters, or the mismatch between observed and predicted satellite galaxies in galactic halos. The so-called missing satellites problem, the lack of visible small galaxies around the Milky Way compared to what models predict, could be partly resolved by accounting for non-luminous satellites that lurk just beyond the reach of our optical instruments. Detecting dark galaxies requires more than visual scrutiny. It demands multi-wavelength observations, gravitational studies, and careful modeling of gas dynamics. Instruments like the Arecibo Observatory before its collapse, and current arrays such as ALMA and the upcoming Square Kilometre Array are critical to mapping these spectral shadows. As technology advances, we edge closer to illuminating what has long remained in the dark. There is a poetic irony to these entities. In a universe defined by light, it is the dark that often holds the most mass, the most influence. Dark matter itself, which constitutes the majority of galactic mass, is invisible. And now, with dark galaxies, we face the reality that entire systems of stars may be ghostly in nature, not in the process of fading, but never having truly ignited. These silent structures, unlit but gravitationally active, are reminders that the cosmos is not limited to what we see. They demand humility in our exploration, a recognition that our senses and tools, powerful as they are, reveal only a narrow slice of reality. The fabric of the universe is woven with both presence and absence, and the dance between the seen and the unseen may be the key to understanding it all. And as we leave these hidden galactic phantoms behind, we are led to yet another cosmic mystery, one where light, rather than being absent, is bent, magnified, and sometimes multiplied. In Outline 16, we step into the extraordinary phenomenon of gravitational lensing, where massive objects warp the very shape of space itself, turning galaxies into cosmic lenses and revealing the deepest secrets of the universe through the curvature of light, galaxy clusters, and the cosmic web, the architecture of the universe. Emerging from the veiled domain of dark galaxies, those elusive, lightless scaffolds of cosmic evolution, we are now drawn outward into the grand design that holds the entire universe together, where dark galaxies represent the hidden microstructures of the cosmos, galaxy clusters and the cosmic web define its overarching form. This is the vast and dynamic framework upon which all matter, light, and movement are suspended. It is a structure that does not merely house galaxies, it organizes them, sculpts their motion, and dictates the paths of energy and time itself. Galaxy clusters are the largest gravitationally bound systems in the universe. They are not mere groupings of a few galaxies drifting near one another, but enormous congregations, often comprising hundreds or even thousands of galaxies, locked in orbit around a common center of mass. Bound by gravity, these clusters are enveloped in colossal halos of dark matter, threaded with streams of hot ionized gas and permeated by magnetic fields and relic radiation. They are not tranquil places. Within them, galaxies crash, merge, and strip one another of gas. These clusters are battlegrounds of evolution, where the past and future of galaxies are written in gravitational dynamics. Each galaxy within a cluster is like a single spark in a roaring bonfire. Some glide quietly through the intracluster medium, while others interact violently, distorted by tides and ram pressure, triggering bursts of star formation or extinguishing it entirely. The environment of a cluster can radically reshape a galaxy's fate. It can strip away the cold gas needed for star formation, turning spirals into ellipticals and quenching galactic youth in favor of ancient starlight. The physics at play within clusters is governed not just by gravity, but by the interplay of radiation, shockwaves, plasma turbulence, and dark matter flows. These vast regions are the laboratories of a vast mesh composed of matter and energy stretching across billions of light years. Along its strands lie galaxies and clusters, while the spaces between, the voids, are eerily empty, almost devoid of galaxies altogether. This web-like structure emerged from the early fluctuations in the density of matter just after the Big Bang. As the universe expanded and cooled, gravity began to amplify these initial imperfections. Dense regions drew in more matter, growing into the filaments we see today. Simulations of cosmic evolution show this process with breathtaking clarity. We looked from a nearly uniform cloud of hydrogen and helium, the universe self-organized into a textured lattice, a universal framework of filaments and nodes where matter congregates and galaxies ignite. The intersections of these filaments are where galaxy clusters reside, often forming superclusters, mighty agglomerations of matter stretching hundreds of millions of light-years across. One of the most massive such structures known is the Lagrangian supercluster, the home region of our own Milky Way. This immense gravitational basin spans over 500 million light-years and contains more than 100,000 galaxies, all flowing toward a common gravitational center. Lagrangian is not a separate entity from the cosmic web. It is a node within it, a swelling along a cosmic artery, part of a vast cosmic river flowing through intergalactic space. The cosmic web also provides crucial insight into the nature of dark matter and dark energy. Since most of the universe's matter is invisible, we detect it not by light, but by its influence. The shape and density of the web, the motion of galaxies along its threads, and the warping of light by its gravitational wells all serve as indirect measures of the dark scaffolding that underpins reality. Even the temperature and density of the intergalactic medium within the web's filaments tells stories of heating by quasars, shocks from gravitational collapse, and the chemical enrichment of the universe over time. In recent years, the cosmic web has come into sharper focus, thanks to sky mapping surveys like the Sloan Digital Sky Survey and space-based observations from missions such as Planck. These projects have charted the positions and motions of millions of galaxies, revealing not a random distribution but a finely structured tapestry. The universe is not chaotic. It is exquisitely ordered at scales that dwarf comprehension. Beyond its scientific significance, the cosmic web evokes a profound philosophical perspective. Its resemblance to neural networks has led some thinkers to draw analogies between the structure of the cosmos and the structure of the mind. While this comparison is speculative and metaphorical, it forces us to ask, is the universe a machine, a living system, or something beyond all categories we understand? The web, with its connections, flows, and branching logic, appears not as a random scattering of matter, but as a deliberate unfolding, an expression of laws deeper than we yet know. And so, from the dark, starless realms of invisible galaxies to the glowing strands of the cosmic web, we come to see the universe as a layered creation, each level of structure building upon the last. It is not a place of mere explosions and voids, but of patterns and architectures, woven with energy and time, forged by the gravity of what is seen and the mystery of what is not. Now, as we trace the light and mass along these cosmic filaments, we are drawn toward yet another phenomenon that bends not just light, but space itself. In Outline 17, we journey into the realm of gravitational lensing, where matter becomes lens and space becomes canvas, revealing hidden galaxies, dark matter halos, and the warp geometry of the universe, the Helix Nebula, the eye of space. From the cosmic web's grand latticework, threading galaxies, matter, and gravitational influence across billions of light years, we now focus our gaze on something far more intimate and haunting. We leave behind the enormous scales of interconnected filaments and plunge inward into the fate of a single star nearing the end of its life. What we find is a structure so delicately beautiful, so eerily symmetrical, that it has been called the Eye of Space. It is the Helix Nebula, a dying star's final exhalation frozen in luminous color, floating in the dark like a celestial iris, staring back at creation itself. Located in the constellation Aquarius, the Helix Nebula is among the closest planetary nebulae to Earth, offering an exquisite view of the stellar death process. But despite its name, a planetary nebula has nothing to do with planets. The term is a relic from early astronomers who, peering through primitive telescopes, saw round, disc-like shapes resembling distant planets. In truth, a planetary nebula represents one of the final stages in the evolution of a medium-sized star, like our own Sun, and the Helix is one of the most well-studied and vivid examples of this cosmic transformation. The story of the Helix Nebula begins with a star that spent billions of years quietly fusing hydrogen into helium, radiating warmth and anchoring a solar system. Over time, as the hydrogen in its core was exhausted, the star grew unstable. Its outer layers expanded, becoming a red giant, and eventually gravity could no longer hold the envelope of gases against the pressure of radiation and stellar winds. The star shed these layers into space, forming expanding shells of gas and dust. What remained at its core was a white dwarf, an Earth-sized, incredibly dense stellar ember emitting intense ultraviolet radiation. That radiation illuminates the surrounding gas, making the Helix Nebula visible. The result is a glowing, multicolored structure shaped by fluid dynamics, magnetic fields, and centuries of stellar winds. The central region glows blue from ionized oxygen, while the outer edges burn red and orange from hydrogen and nitrogen. At the center of this stunning display, the white dwarf glimmers faintly, like the pupil of a ghostly eye. One of the most intriguing aspects of the Helix Nebula is its complex internal structure. What appears to be a simple ring is, in fact, a multi-layered cylinder, an illusion created by viewing a three-dimensional object from a single angle. Advanced imaging has revealed filamentary strands, comet-like knots, and radial spikes of material. all moving outward into interstellar space. These cometary knots, each larger than our solar system, are dense clumps of gas with long, trailing tails pointing away from the central white dwarf, shaped by photoionization and pressure gradients. Their existence was once unexpected and now remains a subject of deep astrophysical interest, as they may influence the final dispersal of the nebula. The helix is not just a pretty sight. It is a stellar autopsy, a snapshot of what will eventually happen to the Sun. Billions of years from now, our star will swell, shed its layers, and become a white dwarf surrounded by a planetary nebula. The Earth will likely be consumed or left as a dead, frozen relic drifting through space. The helix, then, offers not only beauty but foresight. It is a window into both our origin and our destiny. The carbon, oxygen, and heavier elements scattered by the death of stars, like the one that formed the helix, are the very materials from which planets, oceans, and organic life arise. In its death, the star becomes a seedbed for new creation. Observations of the helix across different wavelengths, from visible light to infrared and X-ray, have revealed more than just glowing gas. They show shock fronts, interactions with the surrounding interstellar medium, and the cooling paths of matter as it disperses into the galaxy. This nebula is not an isolated event, but part of a continuous cycle in which stars are born, live, die, and return their elements to the universe, enriching future generations of stars and planets. There is something deeply human in the Helix Nebula's gaze. Across cultures and civilizations, eyes have symbolized awareness, vigilance, and the soul. To look upon the helix is to feel observed by the cosmos itself, as if the universe, through its processes of creation and dissolution, bears witness to its own unfolding. Its symmetry speaks to order within decay, structure within entropy, and its silent light, travelling across hundreds of years to reach us, reminds us that we are part of this grand stellar continuum, that the atoms in our blood once burned in stars and will one day return to them. The helix is more than a structure. It is a metaphor made real by astrophysics. In it, we see the convergence of beauty and finality, science and symbolism. It teaches that the end is not an end at all, but a transformation, a dispersal of being into wider fields of possibility. And as we drift from the eye of space, we are once again invited to look further, not just with our instruments, but with our imaginations. From the disintegration of a single star, we now move to the bending of space itself. In Outline 18, we explore the astonishing realm of gravitational lensing, where gravity becomes not just a force, but a lens that reshapes light and behind the veil of distance and time.